Good afternoon, everyone. It's Professor McDonald. How are you doing today? Hello, Joanna. Hello, Teresa. Hi, Janelle. Hi, Megan. Thank you, Tina. I'm doing well. Hi, Megan. Hi, Natalie. All right, you guys. Hello, Stephen. Hi, Kiana. Hi, Shavsky. All right, so today, um, I do have a few questions from you guys in the inbox. Um, Based on some conversations I was having with some other students last week during office hours, they suggested perhaps instead of just going through questions from the inbox, that I might consider going through the whole guided learning assignment from the beginning. And I thought that might be a good idea. I thought I would share that with you and get a feel for what you guys think about that. Do you think that would be helpful to, instead of just going from question to question, actually go through from the beginning of, say, GLA 12 today? Natalie likes that idea. Shavsky likes that idea. Mackenzie, Stephen. Okay, so it looks like everybody that's responsive is on board with that. Okay, so then let's just go ahead and do that. And then the questions that we have in the inbox, I believe we're probably going to have time to get to those as we go through. Now, there's no guarantee that we're going to get through every single question, because it takes time to explain really, and we don't know what kind of questions you're going to have. So, but we'll try this out today and see how you like it. Maybe you'll like that better, and maybe that can be something we continue to do. So I'm going to go ahead and share my screen, and we'll start working through from the beginning of GLA 12. All right, so this first question involves putting steps in order. So the hypothesis testing process is lengthy, which is what makes hypothesis testing sometimes feel a bit intimidating. And I do have some materials that I think are helpful if you use them as I've demonstrated in the videos. And so I'm just going to open up the reference packet for test 4 for our reference. Okay, so the first thing I want to call to your attention is this hypothesis testing guide form, which really outlines everything that you're going to have to do from start to finish when you do a full hypothesis test, starting from stating your claim and symbols, then breaking that up into your null hypothesis and your alternative hypothesis, determining where your hypothesis lies, because that's significant for when you make your final conclusion at the end, determining once we decide if we reject HO, the null hypothesis, what will that mean about the claim, and whether you're doing a right test, a left test, or a two-tailed test, and also determining whether you're going to be working with z-scores or t-scores. So actually this first box does a lot for getting you started in the right direction, and if you don't get this first set of steps down, you may have trouble doing the rest of it or getting the rest of it right. So I heard a comment. Let me see what you had to say there. Hi, Daniel. I'm glad you made it. Great. So now this says match each step on the left with the procedure at the step on the right. So I would like you guys to tell me what you think step one should be. And I encourage you to also open up that same reference if that might help you, because it is in order here. And you can kind of see it says claim, then hypotheses, tails of the test, sampling distribution. Then you go into doing your curve sketch, and your curve sketch involves, these are numbered, starting with your significance level, then going to your critical value boundary based on your significance level alpha. Then you come down to step 3 and figure out your test statistic by using one of these formulas over here. Then you go on and use that test statistic to find the area in the tail, which is referred to as a p-value, p standing for probability. And remember, probability always means area. So the two things on the left side are areas, and the two things on the right side are boundaries. But this is the logical order that you will find each one of those. 1, 2, 3, then 4. Then you're going on to the decision of whether or not you will reject the null hypothesis. And after that, drawing a final conclusion about the actual claim. Okay, so I'm going to let you guys tell me, based on that discussion, how would you order these steps? Number 1, write the claim in symbolic form. All right, so that's H for number 1. What would be number 2? Write null and alternative hypotheses. Yes. You guys are doing great so far. Okay, so we first identify the claim, write it in symbols, and then break that up into the null and alternative hypothesis statements. Step 3, after you have your hypotheses identified, what will you do next? Yes, identify the test tails. So this involves, this one right here is step 3. This one involves, looking at your alternative hypothesis to determine if you have a left-tailed test, a right-tailed test, or a two-tailed test, and also determining whether this is a test in which you will use z-scores for your critical value in your test statistic, or whether or not those would be t-scores instead, depending on the scenario. All right. So after we've determined the tails of our test and which sampling distribution is appropriate, then we go into doing what? Label the sketch. Well, you do start thinking about how you're going to label the sketch, but is it possible to do that before you have the items that would be labeled on the sketch? Hi, Valeria. So let me open that up again. The reference packet. I want to be able to show just this. I'm going to open that up in PDF form so it's easier to refer to it. Okay, so here's what I was wanting to kind of point out. You're going to be given a significance level in the problem, right? And then you'll use that to figure out the critical value boundary. So it makes sense to me that you would have to go on from, as you're getting ready to label the curve sketch, we're going to need to find these things in order. So the area will be given in the problem, and you're going to use that area to find your critical value. So I'm going to say C is the fourth step. And then where do you go after that? You go from here to here, which would be to calculate the test statistic. And then you're going to use the test statistic to find the p-value, and that is also mentioned in part E, test statistic and p-value. And then at that point, you would be ready to label the sketch with those 4 items, okay, with the 2 areas and their boundaries. So you have a total, you have the red couple, right, the significance, which is an area, and the critical value, which is its boundary. So that's your red couple, area and boundary. Then you have the green couple, your test statistic, which is a boundary calculated from the formula, and then use that boundary to find the attached area. So then you have 2 more, another pair of boundary and area. So all 4 of those will be labeled after you have, identified what they are. So that would be step 6. Okay, let me see where we are with some of your comments. All right, so then after that, now your sketch is labeled. You have the full picture of what your data is telling you at that point, right? So you'll be able to tell if your test statistic is in the rejection region, in the red rejection region or not. And so then you would be able to do what? What would be the next step here? A, reject or fail to reject the null hypothesis. Yes. And finally, we will, is it too obvious? E, so, okay, we already used E. E was to calculate the test statistic, the p-value. We had to do that in order to label the sketch. So yes, writing the conclusion. All right, yes. So F, write the conclusion. Okay, so let's hope everything gets marked correctly there. Okay, very good. Okay, so that is a very important thing to realize, the proper order of everything to do. And again, I highly recommend following this. Like if you were to print this out and just use it every time you do a full hypothesis test, it's meant to be training wheels, okay, to take you through the whole process from start to finish. And then there is also a portion of this to the right where if you are asked to also do a confidence interval, oh, wait a minute, I have it on a separate page. Sorry, it's not on the right, it's the second page, which you have some, if you used this for test 3, you will be familiar with this. So, sometimes you may be doing a confidence interval to accompany your hypothesis test. So it's just another way of analyzing the sample data to use it to estimate the true population parameter. And sometimes that can help either strengthen the results of the hypothesis test, or sometimes it'll dispute the results of the hypothesis test and lead to identifying the need for further research, or identifying reasons why it not have worked out ideally. Okay, so we'll go on to the next question from there. Okay, true or false, sample evidence can prove that a null hypothesis is false? False, says Shavsky. Okay, so only one answer there. Any thoughts on if you agree with Shavsky or why you would agree with Shavsky? Yes, Valeria, we're working on GLA 12 today from the beginning because we were just trying something new today to see if it was helpful to, instead of going, jumping around from question to question, if it might help to just start at the beginning of the lesson and go through one by one. Okay, so no comments to follow up with Shavsky saying that it's false. Well, it's the reason that we say, no, you're correct, Shavsky. Did I make you nervous? No, you were correct. I just wanted to have some discussion about it because do you have a feeling about why that would be the case, or did you read or learn from the lessons why that would be the case? So the reason is that the null hypothesis is only one default assumption that you're looking for evidence to suggest it may be false, that you have significant evidence to suggest it's false, but we are never really proving that it's false. Does that make sense? It's more like the evidence suggests. We want to be careful how we interpret statistical analysis. So, okay, the next question says, below are the hypotheses for a hypothesis test stated in symbolic form by a student who recently took introductory statistics. The sample mean of 100 cases used to implement the hypothesis test is X bar equals 4.2. Which of the following statements are accurate? 1, this is a one-sided hypothesis test. 2, the claim being tested is always about the population, not the sample. So X bar should not be used to state the hypotheses. And 3, the value used in stating the hypotheses should be 4.2 instead of 5. Okay, so let's focus on these one by one. How can you tell if part 1 is true for this example? Would you include this to be one of the true statements? Is this an accurate statement based on what we see here? Would you say that this should be a one-sided hypothesis test, so only one tail? Or, of course, the alternative would be that there are two tails. So which one would you say here, and how can you tell? Based on your participation exercises, what did you learn about how we know if we're doing a left-tailed test, a right-tailed test, or a two-tailed test? What do we look at? I need at least 3 people to answer. Sure, I can ask the question again. How can you tell, what have you learned in the lesson so far? What do we look at so that we know if we will be doing a left-tailed hypothesis test where alpha is all on one side under the bell curve, or if it's right-tailed where it's all on the right, or if we're supposed to split up alpha into 2 equal parts and have 2 tails? What is it that you look at specifically? Yes, so Valeria, you're getting closer. We are going to be looking at a hypothesis. Okay. Steven says the equal sign. You're close, Steven. So between you and Valeria, you're getting in the right ballpark. So let's clarify which hypothesis we should be looking at. We have two of them. Now, what do you know is going to be true every single time when it comes to the null hypothesis symbol? What is always? Right, Shavsky. So we can't look at the null hypothesis to determine the tails because we will have the same equal sign in the null hypothesis every single time. However, the alternative hypothesis will vary based on how the claim was stated, right? So this is where we want to look to tell if we have a left-tailed test or a right-tailed test or a two-tailed test. If it's a not equals symbol, then it doesn't imply greater than or less than, so we have two tails. It could go either way. We're just interested that it's different from whatever the claim is, not in whether it's less than or greater than. So if this was a less than symbol, we would say it was a left-tailed test, and that would be only one tail, one side. If it was a greater than symbol, we would say it was a right-tailed test. But here we don't have any direction, so this is actually a two-tailed test based on the symbol in the alternative hypothesis. All right, so that's not an accurate statement for this example. It says this is a one-sided hypothesis test. We were supposed to identify the accurate statements out of these given statements. So we will not include number one as one of the accurate statements. Okay, so we've ruled out the first one. So let's start looking at the second one here. It says, a little more room here. It says, so as I'm reading this, think about whether or not it's true. The claim being tested is always about the population, not the sample. So X bar should not be used to state the hypotheses. All right, so would you say that number two is an accurate statement? Natalie says that she thinks B is the only accurate statement here. So we have a guess there so far. So Shavsky says yes, Valeria says yes, and I agree with you guys. So what does this symbol here mean? What does the X bar stand for? This symbol. This symbol. Somebody just tell me what X bar represents. Natalie, Valeria, yes, you are correct. The sample mean, all right? And what is the symbol we use for the population mean? Okay, so what symbol would we use for the population mean? It's hard to type it, so I'll just go ahead and answer it. So it's mu, right? The population mean is, and if you were trying to type that, if you had said mu, I would have been happy with that. So yeah, mu is the Greek letter that we use, exactly, the Greek symbol that we use to identify the population mean. Now we're doing a hypothesis test. We're not going to make a claim about the sample. Who cares? We have all the sample data in front of us. There's no reason for us to make a hypothesis about the sample mean because we have it right there in front of us. We know exactly what it is. What we're doing is we're using the sample mean that we've from the sample information to try to understand something about the true population. So your null hypothesis should always have a Greek mu in it if it's a claim about a mean. If it's a claim about a proportion, it would be the p without the hat. So we should not be seeing a sample statistic symbol ever in our hypotheses. Okay, so that one is definitely accurate, part 2 or answer 2. And now let's look at the third one, because we do want to consider whether this might also be accurate. It says value used in stating the hypotheses should be 4.2 instead of 5. So let's read this statement right here, and you tell me whether you think option 3 is an accurate statement. It says the sample mean of 100 cases used to implement the hypothesis test is 4.2. Which of the following statements are accurate? So actually, the only thing we really need to look at here right now is this sentence right here. The sample mean is 4.2. So this says 5, which is not the sample mean, but we didn't want the sample mean in our hypothesis statements anyways, right? We already figured out that this symbol was wrong. We should have had mu in there. So perhaps the 5 would be the claim value. So yeah, part 3 isn't accurate. It's not accurate either, okay? We don't want 4.2 to be in our hypothesis statement, again, because it's talking about the sample, and what we're trying to do is set up a hypothesis that we can support or not support based on what the sample information says. So yeah, 2 seems like the only accurate statement here. And good job on Natalie. She was correct. Okay, let's go to the next one. In an hypothesis test, the decision was made to fail to reject null hypothesis. The null hypothesis was later determined to be false. What kind of error, if any, was committed? Okay, so we should talk about the types of errors that can happen when you're doing hypothesis tests. Type 1 error and type 2 error. Okay, so obviously, if it's called an error, it means a wrong decision must have been made. So there are 2 things that can happen. Let me just put it down here. So either you reject a true null hypothesis in error, right? Because you don't want to reject a null hypothesis that's actually true. Or you could fail to reject a false null hypothesis, right? And I guess I don't have to say in error. It's kind of like, obviously, if you have rejected something that's true, that would be an error. And if you don't reject something that is false, that would also be an error. So which one of these would be type 1? And I had made in the lesson introducing this concept, I had made the point that you can think about your null hypothesis kind of like when you go to jury duty. And if you're chosen as a juror, your responsibility is to view the person who's on trial as being innocent until proven guilty. So if you were to send someone to jail who was innocent, that would be a very serious error. So I'm going to use this as my type 1 error, because that is the most serious error, is that maybe they're telling the truth, but you don't believe them and they go to jail unfairly. I think that's more serious than, say, if someone's guilty and we don't prosecute them, to where they have to pay for their crime. Now, they're both bad things. We don't want to let someone go free if they are guilty of a crime, but as a society, at least here in this country, we've always decided that it's better to be safe and not send someone who's innocent to jail than to really, risk that. It's not worth um, ruining somebody's life when they're innocent, just because you don't want to let someone go free if they are guilty, if that makes sense. So the type 1 error is when you throw out a true null hypothesis. Okay, that's what we want to avoid. We try our best to avoid that. And in general, we try to avoid all errors. But this is why we only try to reject the null hypothesis, and then we have support for an alternative. We don't ever try to accept that null hypothesis. It's kind of like that same thing. Like, if you are assuming someone's not guilty, that's an assumption, right? There's no need to accept it, right? It's just an automatic assumption, and enough evidence needs to be brought forth in order to reject it. Same thing here. We're only talking about if we see enough evidence to reject a default assumption that would otherwise be the obvious thing to just default to. All right, so type 1 error, let's go back to this problem. Now that we've talked about what a type 1 error is and what a type 2 error is, let's read this again. It says, the decision was made to fail to reject the null hypothesis. All right, so being that the decision was to fail to reject the null hypothesis, the only type of error this could be is the second one, which involves not rejecting a false null hypothesis that really should have been rejected, right? So this could be a type 2 error, and let's see. The next part of it says, the null hypothesis was later determined to be false. So we failed to reject the null hypothesis, and it was false, so we really should have rejected it, right? So this would be a type 2 error. Here's another example. So remember, guys, you should try multiple versions of these things if you want to make sure you're getting enough exposure to the concept. I just tried a new version, and it says, in a hypothesis test, the decision was made to fail to reject the null hypothesis, but the null hypothesis was later determined to be true. So this was a true null hypothesis, and the decision was made to fail to reject it, and that would be a correct decision, right? So there would be no error in this case because the null hypothesis was later determined to actually be true. So the right decision was made in that scenario. This one says the decision was made to reject the null hypothesis. The null hypothesis was later determined to be false. So what do you think? Wait, you say no error, okay? We rejected the null hypothesis, and it was a false hypothesis. So yes, that was the correct decision to make. Nice. Okay, good job. I'm just looking to see if we can get another version here. Reject the null hypothesis. Oh, here we go. This time, we decided to reject the null hypothesis. The null hypothesis was later determined to be true. So we rejected a true null hypothesis. What kind of error would that be? Or is it no error? Rejecting the null hypothesis, which turns out to be true. Any thoughts? So we've gone through 3 examples so far, and I gave you the definitions. A type 1 error is to reject a true null hypothesis. A type 2 error is to fail to reject a false null hypothesis. Okay, you want to see the wording again? We rejected the null hypothesis, and it turned out to be a true null hypothesis that we had rejected. Yes, it is a type 1 error. Type 1 error. Okay? This was a true null hypothesis, so it should not have been rejected. And in fact, that is the most serious type of mistake to make. Just like if you were innocent of a crime and the jury rejected your innocence, that would be very serious. So remember, the default assumption is like being innocent until proven guilty. And we don't want to reject that assumption unless there's enough evidence, because we might send someone who's innocent to prison. That works in my mind. You might have to find another way to remember the difference. All right, so let's go on to another question, because we did get to see all 4 versions of that question. Let's go on to another one. You're conducting a left-tailed test of a claim about a population mean when sigma is unknown with a sample size of 29. If alpha is 0.025, find the critical value to 2 decimal places. Okay, now there is a part of this form that may help with this process. Let's go back up here. So this part down here where you identify your significance level, actually, you kind of need to start up here, because you can't go and look for the critical value until you know if your alpha is going to be all in one tail or in 2 tails. So it did tell us already that this was a left test, so we don't have to figure that part of it out ourselves. We already know it's a left-tailed test. And so knowing that, we can jump here. But if you're doing a question where that's not told explicitly, you might have to look at how the claim is stated to figure out, go through the process of stating your claim, stating your hypotheses, and then looking at your alternative hypothesis symbol to see if it's left-tailed, right-tailed, or 2-tailed. But since we do know that this is a left-tailed test, then we can go ahead and start figuring out what our critical value is. I'm going to snip this little portion of the form so that we can go through it together. And actually, I think I would like also the sketch part, because really honestly, just like before I was telling you guys, if you really want to do well on test 3 and test 4, you really need to put yourself in the habit of actually sketching things out every time. All right, so they said a left-tailed test, right? So my significance level is going to be all in one tail, not split up in 2 parts, and my critical value is going to be negative then. Now, let's figure out what the area is there. So this area alpha was given in the problem, as it will always be, 0.025. Now, since everything is in the left tail already, the left area is the same as my total alpha. And I can use that left area to now find my t-score, which will be negative, right? But notice where it says distribution. This is where I choose if it's a z-score or a t-score. Or, you might have already thought about that earlier on in the process. So there's 3 different scenarios that you'll be really focusing on in this course. There are more out there, but we're just focusing on 3 different types of tests. So let's kind of talk about that for a moment. And you've actually already worked with this when you were doing the confidence intervals. So remember, let me connect this back to something you already are familiar with. Remember when you had to choose between these 3 different formulas for your margin of error? And we also looked at another version of this page where we were looking at these 3 formulas here. And the top 2 were for any time you were making an estimation of the population mean, and that's why you see the sample mean as your point estimate starting point. Then you would add and subtract your calculated margin of error. And the third one down was the only formula that would be used whenever we were doing something to do with proportion. So one thing we can do to quickly narrow things down here is to determine if this hypothesis test is meant to be a hypothesis test about a mean or about a proportion, just like we used to do when it came to confidence intervals. And you'll notice that if you slide to the right here, you'll see the corresponding test statistic formulas that go along with the hypothesis test side of things. So your confidence interval formulas on the left, these are your confidence intervals here on the left. Your hypothesis test statistics formulas are on the right, and they are actually correlated. So this is your confidence interval formula for a population mean estimate. And in that same row is the calculation of a test statistic if you were doing a hypothesis test. Same thing down here, we have the formulas for estimating a population mean when sigma is unknown, or if, in other words, you know your sample standard deviation instead of your true population standard deviation. And in that same row, you see the formula for your test statistic. So we just need to first figure out if we're doing a test statistic about a mean. So it would be one of these 2 top formulas, and one of them is Z and one of them is T. Just like over here, this one had Z and this one had T. Your sampling distribution, whether you're doing a confidence interval or a hypothesis test, your sampling distribution is either going to be a Z distribution, meaning your standard normal, or your student's T distribution. So that's what we're trying to figure out right now. So it says you are conducting a left-hand test of a claim about a what? A population mean. So right there, that tells me that I'm going to be using either the Z distribution or the T distribution. If at this point I had read it said a claim about a population proportion, then I would know that it could only be the Z distribution, because when you do tests for proportions and confidence intervals for proportions, you will always be using the standard normal distribution with Z-scores. The only time you might have to use a T-score is if you're doing a claim about a population mean. So if the word mean is in there when it comes to testing a claim, test a claim about a population mean, then you have to consider the possibility that you should be using the T distribution rather than the standard normal Z distribution. Now, how can you tell from there if it should be Z or T? It says here that sigma is unknown. This is your sigma, your population standard deviation. If sigma is unknown, then you couldn't possibly use this set of formulas or the corresponding test statistic formula, right? This calls for a population standard deviation to have been given in the problem. So being that sigma is unknown, you would drop down to this option. And notice that everywhere there are no Z-scores in any of these formulas, but instead you see T scores. So this tells me that our critical value that we are finding here is supposed to be from the student t distribution, not from the standard normal distribution. So now I know that this is my t distribution and that my critical value is a t-score. Now, think back to test 3. How did you find a t boundary when you had a known left area? Oh, wait. I know somebody knows this one for sure. We just had a test on that. How do you find a t-score when you have a known area? What do I do here? Do you have an Excel function that might help us out here to find that t-score? Do you have a table that you like looking at for finding t-scores? It's just the 4 of us, you guys. It's Kiana, Natalie, and Shavsky. Do you have any suggestions? Excel, Natalie? Yes, there is something we can do with Excel. So let's remember the main things that we did with finding critical values before. Remember, we would either, if we were looking for a z-score, we used what did we use to find z-scores? Yes, we would use the alpha in some way, but we do have our alpha. We already talked about that. We do know that we are using our left area of alpha, but how do we use it? Like, in other words, technology-wise, what is the command that I would type into, say, in Excel, if I'm going to start putting in a formula right here to find a t boundary based on this left area of 0.025? How do I find this boundary right here? Okay, so Shavsky, you're close. You said norm.inverse, but norm.inverse would give you a z-score. And we're not using the z distribution here. We're using the t distribution because we don't know our true population standard deviation sigma. Sigma is unknown here. So we can't use norm.inverse because that would give us a z-score. And what we really want is a t-score. So it's not going to be norm anything because norm would imply that it's a z-score. All right, you guys are stumped. Let me show you, let's go back to this table here. This is our reference packet again. You see for t-tests, what does it say? T-tests, t.inverse, right? Look, only for means with s given instead of sigma, or in other words, sigma unknown, we do a t-test, and it has to be left-tailed. You do t.inverse directly on alpha. If it's right-tailed, you do t.inverse on 1 minus alpha. If it's two-tailed, then you're going to do t.inverse on half of alpha, right? So it's t.inverse, guys, not norm.inverse. See the similarity there? Norm.inverse would give you a z-score. T.inverse will give you the t-score. So then you're going to put in your area, which is just the left area. Sometimes, remember, if it's a two-tailed test, don't forget to divide alpha in half for this step. And then the degrees of freedom is always n minus 1. So here it says that we had a sample of size 29. That would mean we have 28 degrees of freedom here. And so that's how we're going to find our p-score. That's our critical value there. And it should be negative, so that's good. I don't need to change the sign on this because it is a left test. And it says to give it to 2 decimal places, so we'll go ahead and round that like this. Whoops. All right. Okay. Let's see what we get if we do a new version. Left test again. Maybe these are all left-tailed tests. Yeah, I'm not seeing anything significant change in here. All of these have said left-tailed test with sigma is unknown. So we'll go on to another question since there aren't any different versions really here except for the numbers changing. All right, here's another one. It says you're conducting a two-tailed test of a claim about a population mean when sigma is unknown with a sample size of 25. Two-tailed test. Okay, now that does change something because last time we were doing a left-tailed test. We're still doing a claim about a population mean. And here again, we see that sigma is unknown. So we're still doing a t-score. So the only real difference here is that we have 2 tails for our claim. And of course, the number on our alpha and our sample size has changed. But we're going to approach this the same way. So the only changes I need to make here on my sketch, I need to change my alpha to 0.1. Okay. Let me get this in here. 0.1. And since this is a two-tailed test, we're going to have to split that up into 2 pieces. So we're going to have 0.05 on each side. So we're going to have a positive critical value and a negative critical value with an area of 0.05 in the left tail and also an area of 0.05 in the right tail. So the left area, which is what we need when we're using our norm.inverse, has to be 0.05. Here, we're not going to have a negative critical value only. We're also going to have a positive as well. And then we'll still use norm.inverse to figure out what the absolute value of those are. So we're going to do p.inverse on 0.05 because that's the left area with we had a sample size of 25, so that would be 24 degrees of freedom. All right, and it does say here to give the positive critical value. So I'm just going to enter this as 1.71. And that's that. All right, here we are conducting a right-tailed test of a claim about a population mean again when sigma is known. Okay, so a couple different things changed here. All right, so let's write in the stuff that has changed. We have alpha is 0.025. This is a right tail test, so it's going to be a positive critical value with an area all in one tail of the total alpha 0.025. And the left area would be 1 minus alpha, right? So we're going to have to calculate 1 minus alpha as our left area. So what is 1 minus 0.025? It is 0.975. All right, so now we have, we also have to choose if we're doing a z distribution or a t distribution. So this is the population mean when sigma is known, right? When sigma is known, This would be a z-test with sigma known, right? So with a right-tailed test, you're doing the critical value is going to be a z-score. So you're going to be using norm dot inverse this time instead of t dot inverse. And the area that you put in is 1 minus alpha, since you had to subtract it from 1 to get the left area. And then you put in your mean of 0 and your standard deviation of 1, because it's a z-score that you're looking for, and z-scores always have a mean of 0 and a standard deviation of 1. So we're going to use norm dot inverse on the left area of 0.975 with a mean of 0 and a standard deviation of 1. And there's my answer. So to 2 decimal places, that is 1.96. All right, so I'm alone teaching to myself. I'm going to go ahead and stop recording here. I hope to see you guys in office hours if I can help you with anything else. And when we meet on, what would that be, Wednesday? Today's Monday, right? So Wednesday, when we meet again, I'm going to take some time to ask you all if you enjoyed this approach of starting from the beginning of a lesson and going through the problems one by one, instead of going through specifically requested questions.